So, we've all spent the last year talking to large language models, but what happens when they learn to see? Today, we're going to pull back the curtain on one of the most exciting frontiers in AI, how these models are developing sight and learning to understand our visual world in a way that's about to change, well, pretty much everything.
I mean, really think about that. Imagine pointing your phone at some cool building and asking, hey, what's the story behind this place? Or, just showing it a picture of what's left in your fridge and asking, what can I actually make for dinner with this? We are moving way beyond AI that just gets text. We're stepping into a world where it understands images, video, sound, a fully multimodal world. And it makes perfect sense, right? When we communicate, it's not just words on a screen. We use our eyes, we use body language, tone of voice, the whole shebang. For an AI to be a truly useful partner in our lives, it has to get all of that other stuff too. These other channels of information are called modalities. So in this explainer, we're going to break down exactly how that incredible leap from just text to actual vision is happening. Okay, so the first giant hurdle is a really fundamental one. Language models, by their very nature, are built for words, for sentences, for text. How in the world do you teach them to process a picture? I mean, a picture is just a grid of pixels. The answer lies in a really brilliant idea called the vision transformer. Look at this picture of a cat. To a computer, this isn't a cute, fluffy animal. It's just a massive grid of colored dots, each with a numerical value. It has zero inherent meaning. Now, language models are used to thinking in what we call tokens, which are basically just pieces of words. So the big question is, how do we get a model that thinks in words to understand this grid of dots? How do we bridge that gap?
Well, the solution is just surprisingly elegant. The Vision Transformer, or VIT for short, does something you could call visual tokenization. It takes the image and it chops it up into a grid of smaller patches. And here's the genius part. It decides to treat every single one of these little patches as if it were a single word in a sentence. And once the image is broken down into this sequence of patch tokens, you can feed them directly into a transformer encoder. And that's the same powerhouse architecture that completely changed the game for natural language processing. So from the model's point of view, it's now just reading a sentence, but the words are pieces of an image. It has effectively learned a new language, the language of pictures. Okay, so the AI can now read the patches of an image. That's a huge step, but it doesn't know what those patches actually mean. It doesn't know that a certain combination of patches represents a puppy or snow. That's the next critical piece of the puzzle, and it's solved by an amazing model called CLIP. So here's the challenge that CLIP was built for. On one hand, you've got your visual data, the raw pixels from an image of a puppy. And on the other hand, you have text data, a caption that literally says, a puppy playing in the snow. These are two totally different kinds of information. How do you teach an AI that these two things, an image and a sentence, actually represent the exact same idea? The secret sauce is a technique called contrastive learning. CLIP gets trained on millions and millions of image caption pairs scraped from the internet. And its job is to create this single shared map, what engineers call a vector space. The goal is to plot both the image and the text on this map, and through training it learns to push the dot for the puppy image right next to the dot for the text, a puppy, while pushing them far, far away from things that don't match. And once you have this shared map of meaning, oh man, you unlock some incredible new powers. You can search for images using plain English. You can find photos that are conceptually similar even if they look different. You can even do something called zero-shot classification, which is identifying things in images it's never been specifically trained on. And by the way, this is the core technology that powers text-to-image generators like Stable Diffusion. It's a huge deal. So let's take stock. We've got the eyes from the Vision Transformer, and we have this conceptual understanding from CLIP. The final step is to hook all of this up to the powerful reasoning brain of a large language model. How do we get them all to work together so you can actually have a conversation about what the AI is seeing? Well, that's where models like Blip-2 come into the picture. Now, the challenge here is pretty significant. I mean, you can't just mash these two giant models together and hope for the best. Training a huge, new, multimodal model from scratch would take an absolutely insane amount of data and computer power. So the question is there a smarter, more efficient way to get these two experts, the vision specialist and the language guru, to talk to each other? And this is where the design gets really, really clever. Blip-2 doesn't reinvent the wheel. It takes a powerful pre-trained vision model and a powerful pre-trained language model,
and it freezes them. It doesn't change them one bit. Instead, it trains just one tiny lightweight module called a Q-former. And this little guy's only job is to be a translator, a bridge, between the two big models. So what this Q-former learns to do is look at the image and pull out the most important visual features. Then it translates those features into a special kind of prompt that the language model can understand. It's basically whispering a super rich, detailed description of the image into the LLM's ear, giving it all the context it needs to reason about it, answer questions, and generate text about what it's seeing.
All right, enough of the theory. We have the eyes, we have the understanding, and we have the brain, all connected by a clever little bridge. Let's see what these multimodal models can actually do.
Okay, check out this great example. A user shows the model a picture of this really sleek, obviously expensive supercar. But they don't just ask, "What is this?" No, they ask a much more complex question, one that needs real-world knowledge. What would it cost me to drive that car? And the model comes back with $1 million. I mean, that is just incredible. It shows it's not just describing pixels. It recognized the car, it connected that visual to its massive database of knowledge about luxury cars and prices, and it gave a direct, reasoned answer. This isn't just a gimmick. This is conversational AI with actual vision. Let's wrap up with a fun one. The Rorschach ink blot test, right? It's famously subjective. It's designed to figure out what's going on in the human mind. So what does a machine with none of our human biases or psychological baggage see when it looks at this? The answer is so fascinating because it's so literal, a black and white ink drawing of a bat. It gives you this little peek into how the model actually thinks. It isn't trying to interpret some hidden meaning. It's just describing the visual patterns that it's learned to associate with certain labels. To the AI, it's a bat, simply because it looks like the thousands of other pictures of bats it's seen before. So, to recap our journey from a bunch of pixels to a real conversation, it all starts with vision transformers, which cleverly turn images into words made of patches. Then models like Clip come in and create that shared map where those visual words meet actual language. And finally, architectures like Blip2 build that elegant, efficient bridge to connect all that visual understanding to the reasoning power of a big language model. And that really brings us to the big question, doesn't it? We are right at the beginning of this incredible multimodal revolution. As AI gets more and more senses, moving from just text to truly seeing and hearing the world like we do, it's not just some small technical upgrade. It's going to fundamentally change how we interact with our technology, with information, and maybe even with each other. The future of AI isn't just about talking, it's about seeing.